In this screencast, we're going to talk about class of solids, specific kinds of solids, in terms of their conductivity. Remember, conductivity is basically a measure of something conducting electricity. And all these things sort of conduct electricity or don't conduct electricity under sort of certain kinds of conditions. So a lot of this is just sort of like semantics. So let us first consider two broad categories of materials, what I'm going to refer to as metals and semiconductors. So a conductor is something that conducts electricity. And metals are very, very good conductors. They basically conduct electricity all the time. So let us consider for a moment two, I know you're not going to like this, but these are molecular orbitals. So very briefly, a molecular orbital comes about from atom number 1, atom number 2. They come together, and instead of having two atomic electronic configurations, we make what are called molecular orbitals. And then we drop the molecular orbitals in, and we learned about back last semester when we were talking about bonding. We talked about how in hydrogen a 1s orbital and a 1s orbital combine to form a sigma 1s and a sigma 1s star, and then we talked about pi and pi stars. If you think about all that, that's all this is, right? So if I have two atoms, I get two molecular orbitals. If I have 8 atoms, so instead of combining 2 atoms together, I actually combine 8 atoms. If I have like a metal, like a bulk solid, I get 8 molecular orbitals. Now you'll see if atom A and atom B are the same atom, and they each contribute, I'm going to have as many filled molecular orbitals as I have unfilled molecular orbitals. Again, in the case of hydrogen, I have my 2 electrons down here, and then my sigma 1s star is open. So if I have 8 atoms, I get 8 molecular orbitals, and the lower orbitals are filled with electrons, and the upper orbitals are empty. So just keep doing this an infinite amount of times with an infinite amount of atoms in a very large solid, if you will. I'm going to have a bunch of molecular orbitals, the bottom ones that are filled, or bonding orbitals, and then I'm going to have a bunch of empty molecular orbitals sort of on top. Okay? So I've got a bunch of electrons down here, and I've got a bunch of electrons up here. So this is what is known as a metal, right? The reason why this is a metal, and this is kind of how conductivity works, in that we have this infinite number of molecular orbitals, we have all these full orbitals, we have all these empty orbitals. When we stick an electron into a metal, what's basically happening is we're adding an extra electron into the particular metal, and it goes into one of these empty orbitals up here, right? Because it goes into this empty orbital up here, it sort of meanders through the metal, and that's how it transmits energy. Basically, conducting electricity is taking an electron from down here in the bonding orbitals and putting it into these antibonding orbitals. In the case of a metal, that energy spacing between here and here is essentially 0, so it takes very little energy to get an electron up here to conduct electricity. Now, an insulator is a different kind of substance. An insulator it's not an insulator that keeps me warm. It's an insulator in that it does not conduct electricity. In the case in an insulator, basically here we have our molecular orbitals, our bonded ones, where here's our electrons, and then here's our empty ones, and notice that we have this gap in energy, which is known as the band gap. And if that gap in energy, remember over here in a metal, the conductivity is I have an electron has to go from here up to here. And so if that energy gap is very, very small, or essentially non-existent in the case of metal, then it conducts electricity very easily and very nicely. If the gap is very, very large, the amount of energy I have to put in to make it conduct electricity is ginormous. It effectively doesn't conduct electricity at all. And then we have this middle ground, what's known as basically a semiconductor. And so a semiconductor is basically a conductor when I want it to be. It conducts electricity when and only when I want it to. So as soon as I put in sort of enough energy, it becomes conductive, right? As soon as I put in enough energy such that if I push the electrons in enough, give it enough initial energy, enough to make the electrons jump from up here to up here, then its conductivity increases and conducts electricity Very, very nice. Again, sort of semantics, we refer to this as the valence band because that's where those electrons are spending most of their time. And then up here we have what is known as a conduction band because the electrons up here are the ones that are going zoom through our particular wire. But again, in the semiconductor, I have to have that amount of energy, so I have to put in that minimum amount. And each semiconductors, you know, every semiconductor that you make has a different band gap. And this is how we make, you know, essentially all the electronics that we're used to today. Computers, calculators, phones, watches, all of those things are built on semiconductors, and that they conduct electricity very, very specifically only when we want them to conduct electricity. So there are natural kinds of semiconductors, so silicon and germanium and carbon as graphite is a semiconductor, and we can synthesize other semiconductors, meaning we can sort of make them in very distinct proportions. And we can almost make semiconductors that have band gaps of whatever we want them to be. Okay, so just real quick before we move on from this slide, in metals, conduction is the electrons going from the valence band up to the conduction band. If it will conduct electricity when the electrons from the valence band jump up to the conduction band. If the gap is essentially minimal, then it will always conduct electricity. If the gap is very large, it will never conduct electricity, and the gap is sort of like halfway in between. It conducts electricity when we want to. This is sort of the gist of all of the electronics that you've ever used before. So semiconductors being an important part of today's society, we actually want them to be very conducive to transmitting electricity. And we can actually increase the conductivity. Now this doesn't change the band gap, but what we're essentially doing is we are tweaking the semiconductor. Because remember how we said the electrons going from here to here are what here's our conduction band. Well, it turns out if we actually add a little bit of impurity, basically make it impure, what we can do is we can actually make it more conductive. Now this doesn't change the band gap, at all, but what it does is it basically says, oh, okay, once it's conducting electricity, it conducts it much more efficiently. And having efficient conduction is actually very, very important, because when the electricity is going through, when electricity goes through wires and such, it generates a lot of heat, right? It's called resistance. We try really hard to cut down on resistance because it's just basically a waste of energy. Resistance is the problem why we have computer fans, that your computer will fry because you've got all those wires in that computer and there's a certain amount of resistance. When the electrons are going down the wire, there's a certain amount of electrical resistance, and that's what's generating that heat. So we want it to be more conductive, right? So by adding the impurities, we're increasing the conductivity, just basically making it more efficient as a conductor. But it doesn't change the band gap, because remember, we want this only turn on when I want, only turn off when I want. So if we add, so this is pure silicon, if we add some impurities with phosphorus, so silicon has 4 valence electrons, and so if this is pure silicon, here's sort of our band gap. But if every, say, 1 per million, for every 1 million silicons, we make one of them of phosphorus. Right, so phosphorus has 1 more valence electron than silicon. So what we'll do is we'll have a couple of extra electrons, right? So our valence band is completely filled. So if we have a couple of extra electrons, then they're going to be up in this conduction band. And so we're going to have some electrons up here. This is known as an N-type semiconductor. We're now going to have some electrons up here. And remember that conductivity is when we go from here to there. And so if there's already some electrons there, when we stick in an electron, there's already electrons in the conduction band, so it zips down the wire much more efficiently. So it takes a very, very little increase in those number of electrons to increase that conductivity. And then of course, if instead of 1 out of every million electrons or atoms instead of a silicon, we put an aluminum, which has 1 less electron, then we're going to be short a little bit. But it turns out this sort of impurity also increases the conductivity efficiency, if you will, and makes them much more efficient. So let's talk a little bit more about insulators. So we know that semiconductors have a band gap of roughly 50 to 300 kilojoules per mole. roughly 50 to 300 kilojoules per mole. And again, we can tweak that to do it whatever we want, whenever we want. Insulators, however, have a band gap that is on the order of over 350 kilojoules per mole. Well, the reason why this is significant is because the amount of energy you basically have to put in to make it conduct electricity is so large that when you put that much energy in, you're essentially breaking it down. So you have to put so much energy into it, it essentially falls apart. So it will rather fall apart than conduct the electricity that you're trying to jam in it. And of course, insulators are, there's natural sorts of insulators. So ceramics are natural insulators. Inorganic ionic solids, which are stable at high temperature. So sodium chloride is an insulator. It's not a ceramic. It's an insulator. Pottery, china, cement, they're all insulators. Some oxides, so aluminum oxide, beryllium oxide. So we have lots of natural compounds, and we can make them. So we can mine insulators, we can synthesize insulators, and of course, we build. Plastics are also great insulators in that we want things that don't conduct electricity often. And our last class material we want to talk about here are what are known as superconductors. Okay, so we had insulators, which don't conduct electricity at all. We have metals or conductors, which conduct electricity all the time. We have semiconductors, who conduct electricity when we want them to, and then we have superconductors that conduct electricity but have no resistance. Right? So we know that all metals have some resistance. We talked about this concept of electrons going down a wire generates a certain amount of heat. Call that resistance. If we can make it such that the electrons flow without any friction whatsoever, this is referred to as superconductivity. And basically, that means superconductivity, another way of putting that is that we have conductance, we have electricity going down the wire or whatever it is, and there is no resistance whatsoever, so it doesn't generate any heat. Superconducting, it's a marriage of, or it's based on what the compound is, what the particular metal is, and what the temperature is. So resistance is also temperature dependent. So you have to have a particular substance that is superconducting, but then you have to drop its temperature below what is known as the transition temperature, or T sub C. Now, superconductors are big and popular and all the rage now because, well, we lose a lot of energy in resistance in terms of heating things up, just pushing electricity down a wire. Resistance is a function of several things, including temperature. It's also a question of the amount of voltage you're putting down it and what the identity of the compound is. So if we can have electrical devices that don't have any electrical resistance, that would be like totally awesome, and that they all conducted electricity, with no resistance. We would save an incredible amount of energy. Just think of how much energy is being used to, how much energy is being used to heat up the surroundings just from your computers running. And we can get really, really, really fast computers. We can get high-speed maglev trains, which are basically big electromagnets. And superconductors are also used in MRI machines, which of course is the cost of why MRIs are so expensive. So there you go. Good luck.